Bismillahirrahmanirrahim. Assalamu alaikum. Last time we discussed the two stages through which the beam undergoes. Today we will discuss stage number 3, which is the final stage of before failure or at the verge of failure. Okay. So you have seen the video last time, and I hope you remember that the beam was cracking, and the cracks were then propagating upwards with the incremental increase in the load. And finally, if you remember, the beam, the concrete in the beam in the compression zone crushed, and then we said that the beam has reached its capacity. Okay. So from the start of the application of the load till the end of the load, you have observed several stages through which the beam undergoes, and the final stage is a stage where the concrete in the extreme top fibers in the compression zone crushed. Okay, and we said that the beam has failed. The beam has reached its capacity. Okay, so what happened at that stage? Let's see. This is the ultimate load. So inside the beam, this is the stress situation. Now at this ultimate stage, concrete in the tension zone has completely cracked, and concrete can no longer resist tensile stresses. All the tensile stresses are resisted now by steel bars alone. However, concrete in the compression zone is there, and it is resisting the compressive stresses. The variation at the final stage of the compressive stresses is not now linear. It is in this shape, which is a parabolic shape. And if we look at this from another angle, from a 2D plane, then we can see that this is a cross section of the beam reinforcing bar that have been placed here. The distance from the top of the compression zone, top of the beam, the centroidal axis of the reinforcing bar is effective D depth. The green area shows the compression zone. The total depth of the beam is H. The width of the beam is B. The white area is tension zone, and the green area is compression zone. Corresponding to this ultimate stage, if we draw a strain diagram, so strain diagram is such that the strain in concrete in the extreme top fibers have reached a value of 0.0003, and strain in steel will depend on the quantity of steel, whether it yields or not. This we will discuss later. Okay, now if you look at the variation of stress through depth of the beam in the compression zone, this variation is parabolic instead of a linear relationship in the previous stages, in stage 1 and 2. This relationship is parabolic. This has been determined experimentally. Okay, and this can be experimentally determined by placing strain gauges here in these locations in the top zone of the concrete, and for every incremental increase in the load, the strains can be measured, and the strain multiplied by the modulus of elasticity of concrete can give us the stresses. So these stresses can be plotted by conducting an experiment on the beam. This is the actual situation in the beam in the compression zone. If we compare the compressive stresses that will finally be produced in the beam to the stress strain curve of the concrete cylinder, we can see that this ordinate the topmost stress. The stress in the topmost fiber is less than the stress in at a depth of at certain depth from the top fibers of concrete. So the maximum stress value is not in the extreme top fibers now at this ultimate state, but is slightly below this. So if we compare this stress now on a stress strain curve, because the stress here is FC and the strain is 0.0003. So if the strain of 0.0003 is taken, then the stress is FC, which is slightly less than FC prime. And in other words, it means that this portion of the top extreme fibers have already crushed. They have reached their maximum value. And now this, the stress at this location, which is at a certain depth from the top fiber, is at FC prime, which is this location. Okay, and the top fibers have already crushed. Because you know that concrete, the compression zone of concrete is basically consisting of some volume of concrete. So unless the whole volume is crushed, we cannot say that only crushing of the extreme fiber will cause the failure of the beam. So for this reason, when the top fiber crushes, still the beam is here to take some load. And after the crushing of the extreme top fibers, then the remaining fibers of concrete, which are at certain depth below this, will be crushing. And the final situation of the stresses in the ultimate stage will be like this. So the extreme top fibers have crushed, they have crossed this limit, and now they are at this stage. The strain is 0.003, and the stress is less than FC prime. The stress now is less than FC prime because it has crossed this stage. At a certain depth below the top fiber, now the stress is FC, okay, and the strain is less. The strain is less. You can see in the strain diagram here that the strain is less than 0.003 at this stage. And for the remaining part of the compression zone, the stresses then keep on decreasing with the decrease in the depth of the neutral axis, and finally the stress becomes zero at the neutral axis, which is not the neutral axis that we the neutral axis at the mid depth of the beam that we discussed in the beginning in the stage 1 or in stage 2. So this is a different neutral axis depth from both the stages. Okay. So this is the situation of the compression zone. On the tension side, what happens, either the steel will yield or not, it will depend on the quantity of steel, and that we will discuss later. Okay, so at this stage 3, the stress situation and the strain situation have been shown in this figure. The strain is 0.0003, as I said earlier, and the stress variation from the extreme top fibers of concrete to the neutral axis is parabolic. It's a parabolic variation. Now, in the previous 2 cases, it was very easy to locate the resultant C, which was the resultant of the compressive forces, because the variation was triangular in the previous cases. So 1/3 from the top of the beam was the location of C. But in this case, since the variation is parabolic, so this exact location is not known to us. This is one thing. The second thing is, now in the previous 2 cases, we said that the total stress acting on this area, which is this green area, is FC. FC was the maximum stress in the extreme top fibers and 0 at the neutral axis. We said that we will be using average stress, FC plus 0 divided by 2. But in that case, the situation was such that the stress variation was triangular. The stress variation was triangular from top fibers to the neutral axis. But in this case, the stress variation is parabolic now, and this averaging of stress will not be applicable. So these are 2 problems that we encountered in stage 3. So in order to simplify this problem, there was a scientist whose name was Whitney. He said that instead of locating the resultant within the parabolic stress variation and then finding the average stress in this area, we can transform this stress into an equivalent rectangular stress variation, and the stress variation in this rectangular area will be such that there will be uniform stress. There will be uniform stress variation, and that will be equal to 0.85 C prime. And this transformation from a parabolic stress variation to rectangular stress variation is allowed by the ACI code under ACI 318.19, 22.2.2.4.1. So they allow this stress transformation from parabolic to rectangular stress transformation in order to simplify the calculations. So if this is done, now the new transformed stress will be like this, and this is basically done with the idea that if we draw a line like this in this, so the total depth of this rectangular stress block will be less than C. Some of the area will be deducted, some of the area will be added, so you will have an equivalent area. So the total area of this rectangle is equal to the area under this parabolic curve. Okay, and the depth of this rectangular block will be A is equal to beta 1 C, where beta 1 is less than 1, so A will always be less than C. C is the total neutral axis depth, actual depth. And the stress over this area, rectangular area, is taken as uniform, and that is equal to 0.85 C prime. And obviously, now the resultant C will act at the mid depth of A. Mid depth of A are at the center of this rectangle. So now this becomes very easy to calculate the resisting moment in this situation. So this stress transformation has been done by Whitney. This is allowed by the ACI code, and this is done to simplify our calculations. And once this is done, we can now calculate the resisting moment very easily, as we have done in the previous two cases. And this time again, the resisting moment will be calculated based on the tension capacity instead of the compression capacity, because concrete is good in compression. Nothing will happen to concrete in compression as compared to the tensile capacity of concrete. So you know now that reinforcing bars have been placed on the tension side, and the total tensile capacity of the beam will be contributed by the reinforcing bars. So the resisting moment will be equal to now T times this lever arm, and this lever arm, which is the distance between these two forces, is equal to LA. And if the total depth from the top of the beam to the reinforcing bars centroid is D, effective D, and this depth is A by 2, so lever arm will be LA is equal to D minus A by 2. So the resisting moment will be T times D minus A by 2, which is written as here. M is equal to T into LA, and T is AS Fy if steel yields. So if steel yields, this will be Fs is equal to Fy, so AS Fy D minus A by 2 will be the resisting moment. Okay, and this resisting moment must be equal to or greater than the applied moment. If you remember, last time I said this quite a few times, that the resisting moment, if the resisting moment is equal to or greater than the applied moment, then the beam will not fail, and the beam will be capable of resisting the applied load and applied bending moment. Okay, so if we equate this resisting moment to the applied bending moment, and we calculate AS from this, if we calculate AS from this, then this AS, if placed inside the beam, will be capable of will enable the beam to resist the applied bending moment M. The problem in this equation is now the A, small a, which is not known to us. Effective D is known because we will assume some size of the beam, width and depth, and we will also exactly know where to place the reinforcement. So this D is known, Fy is the yield strength, M is the applied bending moment, and A is now not known to us. So A can be calculated by equating C to T. If C is, C will always be equal to T, you know this, because if C is not equal to T, there will be a relative movement between the two forces. So C is equal to T, and C, in this case now, what is C? In the previous cases, we said that Fc plus 0 divided by T into the area of, into the compression area. But in this case, the stress is uniform. It is 0.85 C prime, 0.85 C prime, and it is basically acting on this depth now. This is a transform area, where the depth of this area is now small a and the width is b. So the C force that is acting now will be 0.85 C prime, this C, which is the stress, uniform stress over this area, 0.85 C prime multiplied by small a times b. So this will be 0.85 C prime small a times b. This is force and this is area, so force time area is, this is stress, sorry, this is stress and this is area, stress time area is force C. And T is very simple, AS is the area of steel and Fy is the yield strength. So if we equate these two, we can write down this equation like this for A is equal to ASFy 0.85 C prime B. Initially, we can assume some value of A and we can calculate AS. From this, then we can calculate A and we can repeat this and we can run this cycle a few times, 2 or 3 times, and finally we will get the value of S, which will no longer change. And that value of AS, when placed inside the beam, will enable the beam to resist the applied bending moment. Okay. Now, there are some basic assumptions to the mechanics of reinforced concrete beam under gravity load, which have been outlined by the ACI code. And these basic assumptions are not basic. These assumptions are not false assumptions. Assumptions mean that these things should happen. You should clear your concept on whenever we say that these are assumptions before discussing some concept or before deriving an equation. It does not mean that these assumptions are false assumptions. These assumptions means that these things, if these things are there, or if these things are there, or if these things exist, then the theory will be correct. So it does not mean that these assumptions are false assumptions and we are doing something wrong. These assumptions, if I read this assumption, so assumption number 1, that a plane section before bending remains plane after bending. What does it mean? It means that you have seen that the beam undergoes some deformation with the increase in deflection of the beam. So with the increase in deflection of the beam shape changes from a straight member to a curved member. Okay, but this deflection is so small that this deflection will not change basically the shape of the beam from a straight line to a curve for the purpose of calculation of the area or cross-section area of the beam. And this is quite true because these deflections are very, very small. The deflections are very, very small. There are 2 types of mechanics. One is called as small deformation mechanics and the other is called as large deformation mechanics. So far you in your previous almost all courses have discussed the small deformation mechanics, not the large deformation mechanics. The example of a large deformation mechanics is the example of a cable suspended between 2 points. So it will be a large deformation or sag in the cable. So this behavior of the table, if the cable can be explained with the help of large deformation mechanics, not a small deformation mechanics. So the small deformation mechanics in the case of this beam, which is subjected to gravity load, is applicable. And when the mechanics is restricted to small deformation, then the shape of the beam will not change up to an extent which will affect the calculation of areas and moment of inertia of the beam. So this is quite true assumption. And then the second is that stresses and strain are approximately proportional up to moderate loads. When the load is increased, the variation in the concrete stress is no longer linear. This we have seen and we have discussed this, and this is experimental. This has been experimentally proved that the stress and strain relationship of concrete is linear up to almost 50% of the compressive strength of concrete. So if you want to draw a stress strain curve for a concrete cylinder, you will see that the relation between stress and strain is linear up to 0.5 FC prime. Let's say if FC prime is 3000 psi, then up to 1500 psi, the stress will remain linear. The stress will be linearly proportional to strain. But after that, the linearity will not be there. The relationship will still be proportional. Proportionality will still be there, but the linearity will end. And then the stress will be non-linearly proportional to strain, which means that the stress is not proportional to strain power 1. It may be strain power 1.2, 1.3, or even 2. So with every incremental increase in load, then the stress-strain relationship changes. The proportionality is still there, but the relationship is not linear. But up to 50% of the compressive strength, the stress-strain relationship for concrete is linear. The third assumption is that tensile strength of concrete is neglected in the design of reinforced concrete beams. And this is also very true assumption that at the ultimate stage, these things are the assumption that we are discussing right now. Basically, they are associated with the ultimate stage. So at ultimate stage, we have seen that the beam cracks substantially, and the stresses cannot transfer across the crack. So basically, the concrete tensile strength is 0. So if it is taken as 0, or if it is not a false assumption, it is true, and the total tensile strength of concrete, the total tensile strength of this beam is now contributed, or is coming from steel reinforcing bars. The fourth assumption is the bond between the steel and concrete is perfect and no slip occurs. The steel bars are basically deformed bars, and we have seen that they have some projections, and these deformation and projections will help the steel bar to make a good bond with concrete. And it is very important that concrete should make a perfect bond with steel. So for this purpose, the steel shall be placed inside concrete in such a manner that concrete can flow around steel bars, and the concrete is perfectly bonded with steel. So this assumption is also not a false assumption. This will happen normally in concrete. Okay, and if this does not happen, then the theory of mechanics that we have discussed in the previous slide is no more applicable, because the basic assumption in the theory of mechanics of reinforced concrete is that steel is perfectly bonded to concrete, so that the strain in concrete is equal to strain in steel. There is no relative slip between steel and concrete. Okay. Next is the strain in concrete and reinforcement shall be assumed proportional to a distance from neutral axis. This is also very obvious. You have seen in the previous slide that strain in concrete. I will show you the slide once again. The strains. Here, the strain proportionality is like this. This is linearly varying from top to the neutral axis for concrete, and from neutral axis to the extreme bottom fibers for steel. And this is also a very important assumption, and it's also a true assumption, that the maximum usable concrete compressive strain at the extreme fiber is assumed to be 0.003. As I discussed and tried to clarify this concept, that during the test we have seen that the beam was taking more and more load. So before watching this video, your concept of failure about the beam might have been different. And sometimes you would have thought that few cracks, if few cracks are produced in a concrete beam, then the concrete beam will fail very quickly. But we have seen that after the appearance of a number of cracks, and then the propagation of cracks and the widening of cracks, the beam was still capable of taking load. So as long as the beam is capable of resisting the applied load or applied bending moment, it means that the beam has not reached its ultimate capacity. So at the final stage, what happened was that the crushing of concrete in the extreme top fibers of concrete occurred, and then the crushing of concrete in the fibers below the extreme fibers was occurring, and so on, and it was the concrete beam was still capable of taking and resisting load and bending moment. So what will be the final stage after which we can say that the test ends? Okay, and it is now enough, and this is the final stage in the concrete. This is the final stage of concrete, and the concrete beam has reached its ultimate capacity. This is a debatable question. However, because it is a debatable question for the reason that if you now further want to increase the load, you can do so. The beam will be capable of taking some more load, okay, and some more bending moment. And finally, what will happen? I think at this stage we should not discuss those things. I will limit this discussion to the stage that the beam is, although the beam is capable of taking some more or resisting some more load and bending moment, however, this is the ACI code now. The ACI code intervenes, and the ACI code says that no, when the strain in the extreme fiber is 0.0003 and the extreme fibers have crushed and crossed the limit of the maximum stress, then this will be the final stage, and this stage will be taken as the ultimate capacity of concrete. In other words, we would say that concrete has reached its capacity when strain in the extreme fibers on the compression side reaches a value of 0.0003. Although, as I said earlier, if you want to continue your test, if you are doing this test, and if you want to continue the test, you can continue the test, and the reinforced concrete beam will still be capable of resisting some more load and more bending moment. But for the purpose of flexure capacity, there is a limit, and this limit has been fixed by the ACI code. That ACI code says, okay, this is the final stage. We don't need any capacity beyond this limit, and that limit has been fixed not in terms of strength of concrete. That limit has been fixed in terms of strain of concrete, and that strain in the extreme fibers. If strain in the extreme fiber reaches a value of 0.0003, so this is the final stage. What happens to the steel, that we will discuss later. But you should now note down, and you should this point should be very clear to you, that when we say that concrete beam has reached its ultimate flexural capacity, so it means that strain in concrete in the compression side, in the extreme fibers of the beam has reached a value of 0.0003. So this should quickly come to our mind when we say that concrete beam has reached its flexural capacity in stage 3. So we should quickly then think that the strain in the extreme fiber has reached a value of 0.0003. So this is the last assumption of the basic assumptions of the mechanics of reinforced concrete beam theory, which have been mentioned in the ACI 318-19 code under section 22.2. Okay, another assumption. This is another assumption, and this assumption is also very important to note, that what happens to concrete, this we have discussed, but what happens to steel, this we discuss now. That if steel yields, which is what we would like to happen, then the yield strength will be taken as the maximum usable strength of the steel, even though the steel may be capable of taking some more load, and after the yield strength, the steel is capable of resisting load up to the ultimate strength, this you know. And this curve should have been like this. The curve should actually, the actual curve be like this. And this steel is capable of taking some more strength, some more resistance after the yield, and this is called the ultimate strength. But for the purpose of calculation and for the purpose of design, and for the purpose of design, the ACI code recommends that this ultimate strength shall not be taken as the maximum strength of the steel reinforcing bars. The yield strength shall be taken as the maximum. Yield strength shall be taken as the maximum strength of steel bars, maximum strength of steel bars. Okay. And the strain, because the yield strength is taken as the maximum strength, then the strains will be yield strains. The yield strain will happen here. But the ultimate strain will be somewhere here. So, which means that although there is an increase in strain from yield to ultimate, but there is no increase in the strength from yield to ultimate. Okay, although practically there will be some increase from yield to ultimate strength. But this ultimate strength is ignored in our calculation, and this is kept as reserve strength for safety purpose and also for the purpose of ductility. Because this will, if we design and calculate our area of steel based on the yield strength, so we in our calculations would say that the maximum strength of steel is yield, but actually it will be ultimate strength. So after the yield, the steel will still be capable of resisting some more load and bending moment until and unless it reaches its ultimate strength. So this reserve strength is kept for the purpose of safety, and this safety is achieved in terms of ductility of reinforcing bars. Okay. Okay, now we will discuss the strength design method of the ACI code under section 318.19 and 4.6. ACI code says under this section that reinforced concrete member shall be designed using the strength design method. If you remember, last time we discussed two methods. One was working stress method and the other was strength design method. And we also said that in the working stress method, the demand is not increased, the strength are decreased by 50%. In the strength design method, the demands are also increased and the strength are reduced, but both are based on some scientific rationalization instead of arbitrarily reducing strength by 50%. So the ACI code now is categorically mentioned in the code that the reinforced concrete members shall be designed using the strength design method and not using the working stress method. So what is a strength design method? In the strength design method, the loads are amplified, means increased, and the capacities are reduced in this manner. Loads are amplified in the following manner. The load combinations are given under ACI 318.19 5.3. WU is equal to 1.2 WD plus 1.6 WL. What does it mean? It means that dead loads shall be multiplied by a factor of 1.2, which means that dead load will be amplified by 20% or increased by 20%, and live load will be increased by 60%. Why is this difference? Because once the structure is completed and constructed, then the probability of increase in the weight of in the self weight of the structure and some flooring, for example, if there is very, very low. The probability of increase of the dead load is very small, and the probability of increase in live load is comparatively greater than the probability of increase in dead load. Dead load then consists of two parts. One is the self weight of the structure. Self weight means the self weight of the slab, beams, and column, because it is also a dead load. It will permanently stay throughout the life span of the structure. And there is superimposed dead load. Superimposed dead loads are all loads other than the self weight of the structure, which consist of any flooring, for example, on the slab, marble flooring, or plastering, or any other loads which are in addition to the self weight of the structure and which will permanently stay throughout the lifespan of the structure or for a maximum part of the lifespan of the structure. So this they will be called as dead load, and these dead load will be multiplied by 1.2 in order to amplify the dead loads. This is done, the 20% increase in dead load is done for the reason that, for example, a person has constructed his house and then he sells it to another person and he doesn't like the flooring of one of the rooms, for example, let's say, and he replaces the room, or instead of he replaces the floor by completely removing the previous marbles or flooring, or he construct another floor over top of the existing floor. So if he does this, then the load, which is the superimposed dead load, will increase. So this is there is a possibility or probability that dead load may increase in some point of time throughout the lifespan of the structure. So in order to take into account this probabilistic increase in the dead load of the structure, the dead load is multiplied by 1.2. Similarly, in order to take into account the probabilistic increase in live load, the live load is multiplied by 1.6, which means that the live load, the live load is increased by 60%. And the live load, the probability of increase in live load is much more than the probability of increase in dead load. How is this? For example, a building is constructed for the purpose of for a residential purpose, let's say, for a residential purpose. But afterwards, this house is, the purpose of the house is changed to, let's say, to an educational facility like a school, let's say. So you can realize that the school load per unit, per square foot, will be more than the load which are generally encountered in a residential building. So if residential building load is, for example, 20 or 30 pounds per square foot, in a school, it may be 60 pounds per square foot. So the probability of an increase in live load is much higher than the probability of increase in dead load, and for this purpose, these factors have been multiplied. These factors have been probabilistically evaluated by American Society of Civil Engineers, ACI, and they are given in the code, and these factors have been recognized by the ACI code, and these are now used. Previously, these factors were 1.4 for dead load and 1.7 for live load, but then these factors were changed in 2002 code for the first time to 1.2 and 1.6. So this is the background of these codes. Okay, the loads without these factors, the load without these amplification factors, are called as service loads. For example, this WD, which is the dead load without the factor, and WL without this factor, will be called as service loads. Why they are called service loads? Because these are the loads which are the loads that will be applied, or which will be there in the structure during its service. So when the building is serving a purpose, so for most part of its service life, these loads will stay there. These loads will be there. So the load, for example, the dead load of the structure, which is self-weight plus superimposed dead load, will always be there for most part of the lifespan of the structure. They are without factor called a service load. Live load is the load which is taken during the design of the structure with the assumption that this live load will be applying on the structure for most part of the life of the structure. Excuse me, just give me 5 minutes. So the loads without these factors are called as service loads, and when they are multiplied with the factor, they will be called as factored loads. So 1.6 times WL, 1.6 times WL, W is service live load, this is service dead load. 1.6 times WL will be called as ultimate live load. But 1.2 times WD will be called as ultimate dead load. And after they are added together, then the load will be called ultimate load. So this is the explanation to this. WD service load, WS service live load, amplified load is this. This combination is according to the ACI code, and this comes under the heading of strength design method. So in the strength design method, these loads are amplified or increased, but based on a scientific rationale, which I tried to explain to you. If you want some more explanation to this, then this is included in my first lecture, which in my first lecture in the subject of advanced reinforced concrete design, which I teach to master students. Okay, then on the strength reduction factor, according to the strength design method, the resisting member flexure capacity calculated from specified dimension and specified material strength, called as nominal flexure capacity, shall be reduced by multiplying it with strength reduction factor to get the design flexure capacity. You should pay attention to this a little bit now, and after this we can take a little break. That the ACI code says that, as I said earlier, I tried to explain it to you, that the ACI code has fixed the capacity of the beam at a stage where concrete in the extreme top fiber reaches a value of 0.0003 strength. Okay, so corresponding to that stage, we have seen that there will be a C and there will be T. Okay, and M is equal to T times lever arm. This bending moment, this resisting bending moment, which is calculated from the given dimensions or from the dimensions that we are using in our calculations, and the specified strength of the material will be called as nominal bending moment. Nominal bending moment. This resisting moment will be called as nominal flexural capacity. The nominal flexural capacity is basically, if you look at this definition of the ACI code now, the nominal flexural capacity, Mn is equal to ASF by D minus A by 2. And this comes from where? This comes from the specified dimension. Specified dimensions are those dimensions of the beam which we use in our calculations. And the specified dimensions may be different than the dimensions used actually in the field. Okay, because the formwork that we used for preparing a concrete beam, because you know that concrete will be poured inside the formwork and then a concrete beam will be produced. So when the concrete beam is to be produced in a formwork by pouring concrete in the formwork, then it is possible that the size of the formwork is different, slightly different than the sizes of the beam that we have used in our calculation. This is possible. So these dimensions that we actually use in our calculations are called as nominal dimensions, and those dimensions which are finally which comes from the actual beam, the size of actual beam will be called as actual dimension, which will depend on the formwork, and the dimension which we use in our calculation are called as nominal dimension. So the nominal capacity is basically calculated from the specified dimension or the dimension that we use in our calculations. Okay, these dimensions we would like to be achieved as it is in the field, but it is not always possible, because concrete beams are produced in the field. In situ concreting is done, so there are a lot of uncertainties in the formwork that we provide to the concrete beam. The formwork that we place for the concrete beam production may have sizes different than what we have used in our calculations. So you should remember that nominal flexure capacity is the capacity which comes from the dimension that we use in our calculation. They are called specified dimension, and the specified material strength. Why specified material strength? Specified material strength is for let's say we are using grade 60 steel, so the specified yield strength of the steel is 60 KSI. But this is not actual. Actual will come from the test. If you test a steel sample, so you may encounter or you may determine steel strength, yield strength, which is different than this yield strength. Most of the time it will be greater than this yield strength, but it will not be 60 KSI. It may be 61 or 62 or 63. But the Mn nominal moment is calculated from 60 KSI, not from the actual test, because we cannot do testing on each and every sample of the steel bar. So the specified dimensions are the dimensions that we use in our calculations, and the specified material strength are for concrete, it is the FC prime that we would like to achieve in the field, but it may not happen due to some uncertainties in the field. And for steel, it is the 40 KSI for grade 40 steel and 60 KSI for grade 60 steel. Then this nominal bending moment, nominal flexure capacity, the nominal flexure capacity is taken as Mn is equal to As Fy d minus A by 2. And then this nominal capacity, for the purpose of calculation of area of steel, we reduce by 10% and we multiply this by 0.9. So the design capacity that we will use in our calculation will be 5 times Mn, 5 times Mn, or 5 pi A SFYD minus A by 2, and this phi is taken as 0.9. So the phi Mn or MD shall be greater than or equal to Mu. This is the strength design requirement. MD, which is the design capacity, shall be greater than Mu. So when we equate MD to Mu, if MD is at least equal to Mu, then AS will be equal to the phi 0.9 will come in denominator, Fy d minus A by 2. So when phi comes in denominator as 0.9, it will increase area of steel a little bit. And this little bit increase in area of steel is necessary for the purpose of factor of safety. So we have increased Mu by amplifying dead load and live load, and we have reduced nominal moment. We have reduced design moment by 10% by multiplying the nominal moment by 0.9. So area of steel will be increased by increasing Mu and by reducing the nominal the design strength. So the 0.9 factor will also increase AS and Mu will also increase AS. So finally we will get a value of AS which will have an inherent factor of safety because we have increased Mu and we have reduced the flexure capacity of the beam by 10%. Now we will take a little break of 10 minutes and then we can continue our lecture. Okay. Okay, let's continue lecture. Okay, the nominal flexure capacity of reinforced concrete member according to the ACI code. As I said earlier, that the ACI code has fixed a limit to the nominal flexure strength of RC member, and that limit is in terms of strain in concrete instead of strength of concrete or steel. The ACI code the exact statement of the ACI code is mentioned under section 21.2.2, which says that the nominal flexure strength Mn equal to A SF by D minus A by 2 of a RC member is reached. Okay, when the strain in the extreme compression fiber reaches the assumed strain limit of 0.003. So the nominal flexure strength, which is the maximum strength that you can achieve from a beam, is at a stage where strain in the extreme compression fiber reaches the assumed strain limit of 0.0003. So this is the nominal flexure capacity. In other words, the beam finally fails by crushing of concrete, even if steel in tension has yielded well before crushing of concrete, or even if steel has not yielded. Okay, now what happens to steel? This we will discuss right now. We have now very clearly said, categorically said that we would say that the beam has reached its capacity when the strain in the extreme compression fibers of concrete reaches a value of 0.00. So this is on the compression side. What happens to the steel now at this stage? There are three possibilities. Either the strain in reinforcing steel bar is equal to yield at that particular instant of time when strain in concrete is 0.0003, or strain in steel reinforcing bar is less than the yield strain at that particular instant of time when strain in concrete is 0.0003, or strain in steel is more than yield strain at that particular instant of time when concrete strain is 0.0003. Okay, what are the implications that that needs discussion now? If strain in steel is equal to yield strain at that instant of time where strain in concrete is 0.0003, when strain in concrete is 0.0003, what does it mean? It means that concrete has crushed, so the concrete capacity is gone. But the steel is equal to yield. So what will be the situation, actual situation at this stage? You have seen in the video that yielding of steel will be coupled with the deflection of beam, which means that with incremental increase in the load, when yielding of the steel occurs at the final stage, then the deflection will be very visible in the beam, and this deflection in the beam and the cracking in the beam will help us to vacate the building, and we would be in position to say that the building is not safe or the building is unsafe, because the beams have substantially bent and the beams have substantially cracked. So there, the visible deflection and cracking of the beam will be only there if steel yields well in advance, well before the concrete crushing. But if this yielding and concrete crushing occurs at one and the same time, then the visible deflection or visible sag in the beam and visible substantial cracking of the beam will not be there, which is not good. Okay, and similarly, when steel does not yield, which means that the strain in steel is less than the yield at particular instant of time when concrete reaches its maximum limit, then obviously there will be no substantial deflection of the beam. There will be no even cracking of the beam. So there will be the final failure will be just a brittle failure. So in cases 1 and 2, the failure will be a kind of sudden failure, a brittle failure, and this will not give us enough time for evacuation of the building, which means enough time for escape or degree of warning. So, and we would like that when the building is at the verge of failure, so before failure, we get enough time to evacuate the building, which is called as safety time or degree of warning or escape time. So this escape time can only be ensured if steel yields well before concrete crushes. Okay, because the yielding of the steel will produce more and more deflection and sag in the beam, and which will be very visible with naked eye. And by looking to the beam, we can say that the building is now unsafe, and we can evacuate the building. So this concept in the design is called as the ductility concept, and the ACI code would like the ACI code is recommended. The ACI code proposes that if ever a failure occur, it should be ductile failure. Okay, if ever a failure occur, it should be ductile failure instead of a brittle failure. And for this purpose, the ACI code has put a restriction on the maximum quantity of steel to be used in a beam. Because if you look at these 1, 2, 3 conditions, they will depend on the quantity of steel. If quantity of steel is relatively speaking, if quantity of steel is less, then yielding will occur because the strength of steel will be less. So when the strength of steel is less, yielding will occur. Okay, but the strength of steel will not be less up to an extent where the steel will not be capable of resisting the applied bending moment. The applied bending moment will be resisted by the steel bar successfully, but if the quantity of steel is very high, then the steel will not yield at the ultimate stage, and concrete will be crushed, and it will lead to a sudden failure. So for this reason, the ACI code says that, okay, you can place reinforcement in the form of steel bars on the tension side, but this reinforcement in the form of steel bars shall not be greater than a value which would not allow yielding of the steel, So yielding of the steel must be allowed before crushing of concrete, which is a desirable mode of failure. This is called a desirable mode of failure or ductile mode of failure. Okay, next I will discuss with you the strains of steel bars. This is a grade 40 steel curve, and the yield strain of grade 40 steel is 0.0013, and this you can very easily calculate. 40 divided by 29,000 will give you yield strain of grade 40 steel. For grade 60 steel will be 0.002 because it will be 60 divided by 29,000, and so on. Okay, this is for grade 75 steel, and this is for grade 90 steel. In Pakistan, we generally use nowadays we use grade 60 steel. So for grade 60, it is 0.002 strain. Okay, it is 0.002. Yield strain of grade 60 steel is 0.002. Okay, 0.002 strain. Okay, now the ACI code, as I said in the previous slide, that the ACI code would like that steel yields well in advance of concrete crushing, or the value of strain reaching a value of 0.0003. So how this can be achieved? This can be achieved by putting a restriction on strains of steel. If we fix the strain in steel, if we fix the strain in steel such that it is always greater than the yield, then and we couple the quantity of steel with the strain greater than yield strain, then whatever the quantity of steel is obtained after calculation will always be such that it will ensure the yielding of steel. So this is what exactly been done by the ACI code. The ACI code says that you should place reinforcement inside the reinforced concrete beam such that the maximum amount of reinforcement that you can place inside the beam is such that the strain in steel on the tension side is equal to yield strain of that bar plus 0.0003. And you know that plus 0.0003 is the strain, maximum strain value in the extreme compression fibers of concrete. So this 0.0003 plus the yield strain shall be the minimum strain in steel, minimum strain. The strain in steel cannot be less than this value. And this is to make sure that the steel yields or the steel has yielded, because the yield strain is ETY. So the ACI code has not said that the strain in steel shall be equal to the yield strain when concrete reaches a value of 0.0003 on the compression side. But it says that it should be yield strain plus 0.0003 in order to make sure that the steel has yielded well before concrete reaches a value of 0.0003. Okay? And then if we now calculate the area of steel corresponding to this condition, if we calculate the area of steel, and then this will be the maximum area of steel that can be placed inside a particular beam of given dimensions. Okay, this I will try to explain a little bit because this becomes difficult for the student. But let's say there is a beam of a given size B and H, and we equate C equal to T, and the conditions are such that the steel has yielded, so F is equal to Fy, and C is equal to 0.85 C prime AB. For this condition, we know that at ultimate condition, this value will be 0.003. Okay, and this value, this ES value shall be equal to ETY plus 0.0003 at ultimate. And if corresponding to this condition, we calculate this AS, and we call this AS 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 maximum, then when this AS maximum is placed inside this beam, this will for sure produce yield strain, produce strain greater than the yield strain. And when AS is less than AS maximum, it will also produce strains greater than this yield strain plus 0.003. However, if AS is more than this AS max, then the strain in steel may not be equal to or greater than this, or less than or greater than this value. Less values are not desirable. More values of ES, more values, because more value means more yielding of steel, more yielding of steel. If I once again show to you this stress strain curve now, so according to the ACI code, if yield strain is now, this is the yield strain of grade 60 steel. This is the yield strain. Sorry, this one. This is yield strain for grade 60. So according to the ACI code, the strain in steel shall be equal to 0.002 plus 0.003, which means 0.005. So it will be somewhere here. So yielding of the steel, this much yielding of the steel would have occurred when concrete reaches a value of 0.003, which means substantial yielding would have occurred. So if yielding is more than this, that will be okay. That will be a desirable situation. But if strain in steel is less than this, that will be undesirable situation, not leading to a ductile failure. Okay, so now we will, with the help of this strain diagram, this is the strain diagram now, where this is the neutral axis depth C, and this distance is D minus C now, this is D minus C. And if we, by similarity of triangle, calculate C now, which is C divided by EU from this triangle, C divided by EU. And this triangle, which is D minus C divided by ES, and we calculate C, we know EU, which is 0.003, we also know ES for certain grade, actually for grade 60 it will be 0.0005, okay, because the yield strain of grade 60 is 0.002. So we can calculate C in terms of D, and this C, neutral axis depth, from this C we can calculate small a, and once small a is calculated, we can calculate AS from this equation. And that will be the maximum AS which can be placed inside a beam, and the value of AS can not be more than AS max, as per ACI code, because then this criteria of ES is equal to ETY plus 0.00 will not be achieved. So then ES is equal to ETY plus this, EU is 0.0003. For a grade 640, it will be C is equal to DEU divided by this. So this will be EU is 0.003, this is the 0.003, and ES, which is the this thing. Yield strain of grade 40 is 0.0138. So 0.0138 and 0.003, when they are at it, will give you 0.00438. So that 0.00438, if it is substituted here, you will get C in terms of DHG, C is equal to 0.41D. Okay, and then A can be calculated from this. A is equal to beta 1C, and beta 1 we will see next. In most of the condition, it is 0.85 if FC prime is less than 4000 psi. Similarly, for grade 60, C will be equal to D like this, and then C comes out to 0.370 because this ES comes out to 0.005, and A is equal to beta 1, C can be calculated from this. Now, when this value of A is substituted in the equation, for AS, this will become AS max. This is the maximum area of steel that can be placed inside a beam of given dimension B and D. So this AS max can be now calculated for any B and D, knowing beta 1 and Fy. So that will be the maximum value or limiting value of AS that can be placed inside a beam of given dimension in specified strength. For the simplification of this, beta 1 is equal to 0.85 when FC prime is less than 4000 psi. So this will give us this equation: 0.3 FC prime divided by FYD for 40, grade 40 steel, and AS max is equal to 0.27 FC prime. I will ask you now just to calculate AS max for a beam with total dimension B equal to 12 inch, B equal to 12 inch, and H is equal to, let's say, 21 inch, but effective D is, let's say, 18 inch. Let's say, excuse me, this is 24 inch and this is 20 inch. So can you calculate now AS max for grade 40 and 60 and tell me what are your values quickly, please? Given this FC prime is 3 KSI and Fy is 60 KSI. Fy is 60 and 40 both. Can you do this, please, quickly?
फर्स्ट वन 5.4 आता है सर.
कितना आता है?
5.4.
FC आपने कितना लिया है?
सर FC 3
KSI ले लेना. Fy 60.
यस सर. The first one सर 40 वाला Fy 40 लिया है
जी.
Fy 40 लिया है सर.
दोबारा बताएं आप.
सर मैंने Fy 40 लिया है और FC 3 लिया है. 5.4 आता है.
FC आपने 4 लिया है. FC प्राइम कितना लिया है? कंक्रीट की स्ट्रेंथ कितनी?
3 लिया है सर. 3 लिया है. 3 KSI.
और Fy कितना लिया है?
40 KSI.
अच्छा, उससे कितना आता है?
5.4.
अच्छा, एनीवन एल्स?
यस सर 5.4. यस सर 5.4 ही आ रहा है.
तो इस, अच्छा, आप दूसरे के लिए मालूम करें.
सर 3.24 आ रहा है.
अच्छा, आपका क्या नाम है?
मोहित इरफान.
मोहित इरफान, मुझे ये बताएं कि अब ये हमारे पास AS max आ गया, तो इस ये हाउ इज दिस इंफॉर्मेशन यूजफुल फॉर अस नाउ?
सर ये मैक्सिमम एरिया ऑफ स्टील है जो हम यूज करेंगे सर बीम में.
अच्छा, और उससे जी प्लीज और बताएं.
बस सर जब ग्रेड 40 स्टील होगा, जब ग्रेड 60 होगा, डिफरेंट उसकी दोनों के लिए डिफरेंट मैक्सिमम एरिया ऑफ स्टील हमारे पास आ गया.
अच्छा, और अगर हम इससे ज्यादा AS इस्तेमाल करें तो फिर क्या होगा?
सर ज्यादा इस्तेमाल करेंगे तो फिर मतलब और बर्डन होगा वैसे तो स्टील का. और
व्हाट विल बी द outcome of this more area of steel.
सर
Anyone
फेलियर
else?
बिहेवियर ब्रिटल रिडक्टाइल वो होगा.
हाँ बिल्कुल ठीक है. बस का फेलियर जो है वो अनडिजायरेबल फेलियर जो ब्रिटल हो जाएगा, यानी यील्डिंग नीचे नहीं होगी या कम होगी, डिपेंडिंग ऑन द क्वांटिटी ऑफ स्टील. कितनी आप बहुत ज्यादा डालेंगे तो फिर तो यील्डिंग भी नहीं होगी, लेकिन अगर थोड़ी सी ज्यादा डालेंगे तो यील्डिंग तो हो जाएगी लेकिन सब्सटेंशियल यील्डिंग नहीं होगी, which will not give us a substantial degree of warning or escape time. समझ रहे हैं आप?
यस सर.
ठीक. अच्छा, अब आप नेक्स्ट हम एक और चीज डिफाइन करते हैं, which is called as reinforcement ratio. Reinforcement ratio is basically the ratio of area of steel to the effective area of concrete. And effective area of concrete is taken as B times D, which is not the actual total area. Total area is BH. This is the effective area. This is reinforcement ratio. So for maximum reinforcement ratio, we can write rho max is equal to AS max divided by BD. And we have calculated that for grade 40 steel, AS max comes out to be 0.0225 times BD. Okay. So if this value of AS max is substituted here, this will be 0.0225 BD divided by BD. BD will be cancelled with BD, and we will be left with 0.0225, which means that 0.0225 or 2.25% of the effective area of concrete is the maximum reinforcement that we can place inside a beam of given dimension. 2.25% of the effective area of concrete. So for example, if the area of concrete is 100 square inch, 2.25 square inch of steel is the maximum area of steel that can be placed inside the beam. If it is 200 square inch, 2.25 multiplied by 200 is the maximum area of steel that can be placed, but for grade 40 steel. For grade 60 steel, the same simplification will give us a value of 1.35% of the effective area. So for the same size of beam, the maximum area of steel for grade 40 steel will be 1.35% as compared to 2.25% for grade 40 steel. Okay, 1.35%. For example, let's say a beam has an area of 100 square inch cross-sectional area, so 1.35 square inch of grade 60 steel can be placed inside this beam in order to achieve a ductile mode of failure. Any area of steel more than this will give us a brittle failure, and it's not allowed as per ACI code. Next, I will show you a video which is about a beam which has been deliberately designed such that AS is greater than AS max. So in this beam, the area of steel that you placed inside is more than maximum area of steel. Last time, if you remember, I told you that if some of you are interested in doing a project on a similar line, so you can do this. When this project strain gauges have not been installed, but you can install strain gauges. You can also draw stress strain curve and do some more testing. It will be very interesting to see the actual strain behavior that you determine from the beam testing. Okay, so you have seen that this beam behavior is different from the beam that we have watched in the previous video. From the point of view of deflection and the crack patterns, there was no yielding. If you have noticed in the stress strain curve, that yielding of steel does not occur. So this behavior is an undesirable mode of failure if you compare this with the standard beam that we have seen in the beginning. Okay, ACI code has also placed a limit to the minimum reinforcement. The minimum reinforcement shall not be less than the values given in the equation A and B, and the greater of A and B shall be selected for this purpose. If you look at these values, one of the equation is 3 times FC prime divided by F5BD, another is 200 divided by F5BD. And if you substitute the value of FC prime equal to 4,500 psi, then this value in the numerator comes out to be 200, almost 200. So equation B will give you greater value than equation A as long as FC prime is less than 4,500 psi, which is mostly the case. But if FC prime is more than 4,500 psi, then this equation will give you greater value. You can check these values. And from where these values are derived, this can be done very easily. If you remember, in this, we said in our discussion in stage 1. In stage 1, if you remember, stage 1, we said that the compressive stress C will be equal to 0 plus Fc by 2, which is the average stress times BH by 2, which is the area, compression area. So C will be equal to FC BH by 4. Correct? Okay. And T corresponding to this stage, the tension in the tension side, on the tension side, T in concrete will be equal to Ft BH by 4. And this Ft is the modulus of rupture, 7.5 times Fc prime. So we should not place reinforcement in the reinforced concrete beam, which should give us a tensile strength less than this, because this is a tensile strength of concrete. So if reinforcement is less than this, it is of no use to us, because concrete will crack and the steel will yield very quickly and suddenly, and the cracks will propagate and shoot upwards, and the beam will split into pieces. So the area of steel that we provide in the reinforced concrete beam shall not be less than the tensile capacity of concrete. This is the tensile capacity of concrete. If we equate this now to ASFY, which is the strength tensile stress in steel, tensile force in steel. So this is the tension in steel, and this is tension in concrete. If we equate these two and we calculate this AS, so that this AS is called as AS minimum, because this should be AS minimum and we should not place AS less than this. Then this Ft, we know it 7.5 times Fc prime. Fc prime. Okay, Ft 7.5 times Fc prime into BH divided by 4 and divided by Fy. Okay, if you compare now this equation, with this one, what is the difference? 7.5 divided by 4 is equal to how much? 7.5 divided by 4 is
1.875.
1.875. And in this equation, we have D, and here we have H, and H is greater than D. You know this because H is total depth. So if H is expressed in terms of D, and if it is, let's say, taken equal to 1.8 times D, 2 times D, so it will be if it is 20% more than this, then 1.2 times D, 1B multiplied by 1.2 times D multiplied by 7.5 divided by 4. What will be the value? What is the value? 1.2 times 7.5. Comes out to be 2.25, okay? And this value is 3. So this value is being rounded up to 3, so that area of shield is slightly more than this thing, slightly more than this, okay? This slightly more than this. So AS is equal to 3 times FC prime divided by 5 by D has been derived in this way. And this is the minimum area of steel that can be placed inside a reinforced concrete beam. Even if the requirement is less than this shall be always provided. Okay. Next, we move ahead with another video that will show you the behavior of a beam where the reinforcement is less than the minimum reinforcement. Okay, so you have seen that this beam behavior is also quite different from the one that you watched in the beginning. It was a standard beam. This beam was having reinforcement less than minimum reinforcement. You have seen very wide cracks in the beam, and the beam shooted upwards very quickly. And when the steel yields and the capacity of the steel is almost equal to or even less than the concrete tensile strength, then it gives us a very premature, sudden brittle failure. So it is an undesirable mode of failure. Okay, having said that, now finally we can evaluate and calculate the minimum and maximum reinforcement ratios for different strength of concrete and yield strength of steel. For a 3000 FC prime and 40 and 60 grade, minimum reinforcement is 0.0005, which means 0.5% of the effective area of concrete. For grade 40 steel and 0.33% or 0.03% of the grade 60 steel. And similarly, it is 2.25% maximum reinforcement for grade 40 steel when FC prime is 3000 psi, and 1.35% if it is grade 60 steel. For FC prime 4000 psi, there is no change in minimum reinforcement for 40 and 60 both. However, there is change in maximum reinforcement. For the grade 40 steel, it becomes equal to 3%. It increases with the increase in FC prime because concrete will become stronger. So a stronger concrete, then you can place some more reinforcement on the tension side. And then 1.8% on the for the grade 60 steel for 5000 psi, the minimum reinforcement changes to 0.0053. There is slight change, not a substantial change, but there is substantial change in maximum reinforcement, 3.5% and 2.1% if FC prime. So with the increase in FC prime, there is change in maximum reinforcement, and there is a very small and insignificant change in the minimum reinforcement. You can remember these. You should remember all these values so that you can readily use these values in your design examples that we will be doing at the end of this lecture. Okay, now having discussed all the necessary theory and mechanics of reinforced concrete structures and the ACI Code recommendations pertaining to the flexural capacity of reinforced concrete beams, we will now discuss the steps necessary for the design of a beam. Okay. First of all, we will select appropriate size of the beam. By size of the beam, I mean the width and depth of the beam. Then the loads will be calculated, and then the beam will be analyzed and finally designed, and drafting will be done at the final stage. In the selection of sizes, there are two things. One is the width of the beam, another is depth of the beam. Width of the beam is generally taken taken on the criteria of the maximum number of bars that can be placed in one row in a beam that we will discuss in the coming slides. But depth of the beam, for the depth of the beam, the ACI code has given a criteria that if the beam is simply supported, then in the beginning, the depth can be assumed equal to L by 16. For example, if a beam is 16 feet long, center to center from this, for the simply supported beam, then the beam should be at least 1 foot deep. The total depth should be at least 1 foot. But this is, mind that this is the minimum requirement. And these equations have been derived based on the deflection control criteria. You would have seen in the previous several slides that while we were calculating area of steel, there was no check on the depth of the beam. But there must be a check on the depth of the beam, which means that there must be some minimum depth of the beam in order to control excessive deflections, because the beam may not fail actually due to the quantity of less quantity of steel reinforcement, but it may excessively deflect And the excessive deflection will cause a psychological pressure on the occupants, and for the psychological reasons, it is not recommended that the beam during its service life undergoes excessive deflection. So in order to avoid excessive deflection, some minimum depth have been recommended by the ACI code, and this ACI code has given this equation for simply supported beam is for 1 in continuous. If 1 in continuous, then the depth needed is less than the simply supported, because the continuity will help the preventing the excessive deflections along with the depth of the beam. And if both ends are continuous, then still even more shallow beam will be enough, because the continuity on both ends will help keeping the deflection within the limits. If it is a cantilever beam, then the deflection will be excessive, and the deflection, excessive deflection can be controlled if the depth of the beam in the beginning is taken equal to L by 8, which means that if it is 16 feet long beam, so 16 divided by 8, 2 feet deep, at least 2 feet deep beam will be required if it is cantilever. Okay. These equations can be multiplied by 0.4 plus Fy divided by 100,000 if grade 6 steel is not used. Okay. If any other grade steel is used, then this will be multiplied. It means that if you use grade 40 steel, this deflection can be slightly reduced. Then calculation of loads. Dead loads can be calculated from the self-weight of structure and superimposed dead loads. Live load can be calculated from the recommendation of the ACI code for depending on the occupancy of the structure. If it is hospital, if it is office, if it is residential building, analysis can be done. You have learned the analysis procedure. You can do analysis of beam very easily if it is simply support after it continues. Once analysis is done, the bend, the design is done for the maximum bending moment. You should also note down this, that we do design for maximum bending moment for the maximum value. And then the design is done in hit and trial method using the Whitney's stress transformation block by equating M is equal to ASFY and then AS is equal to MU, where MU is now, you know that MU is what? MU is the applied or the resisting bending, it is the ultimate bending moment, which comes from MU. MU is equal to 1.2 MDU plus 1.6 MLU. Dead load and live load are both factored to give us MU. Then after trials, assume small a, and calculate AS, then calculate this, then substitute this value of AS in this equation, do trials, and after 2 trials you will get the value of AS which is required. And this AS shall be then compared with AS max and AS minimum. And this calculated AS shall fall between AS max and AS minimum. If it is more than AS max, it is not recommended, then mostly you will have to increase the size of the beam. And if it is less than the minimum reinforcement, you will have to provide the minimum reinforcement at least, not this reinforcement, if it is less than the AS minimum. These are checked for AS maximum and minimum. You will check your AS with this. And then finally, if area of steel calculated falls between AS max, falls within the range of AS max and AS minimum, then the number of bars will be calculated based on this total area of steel divided by the area of bar that you would like to use. You would remember that we studied different diameter of bars that are available in the market, and from that diameter of the bar you can calculate area of individual bar, and that total area of steel, if divided by individual area of the bar, you will get total number of bars, and number of bars will always be rounded up. These calculated number of bars must be placed according to the ACI code criteria, which is discussed next. How to place these bars? These bars shall be placed such that there is a cover of at least 1.5 inch on all sides. If this is the bar that we are placing, we will always need a stirrup in this form. These stirrups are provided to resist shear forces. So the clear cover from the edge of the beam, or from the bottom or top of the beam, from all sides of the beam to this exterior face of this reinforcing bar shall be at least 1.5 inch clear. 1.0. So 1.5 inch cover should be provided on all sides with the reinforcing bars. Okay, 1.5 inch. This is one requirement of the ACI code. The second requirement of the ACI code, that bar shall be placed not closer than 1 inch or diameter of the bar, or 4/3 of the maximum size of the core segregate, whichever is greater. So, for example, you are using number 8 bar, which has a diameter equal to 1 inch. The aggregate size is, let's say, 3/4 inch maximum size. Then 4/3 multiplied by 3/4 is also 1 inch. So 1 inch, 1 inch, 1 inch. You will at least place your bars at a spacing of 1 inch. But I would suggest to you, in the Pakistani context, that this spacing shall not be less than 1.5 inch. What is this? What is the advantage of this spacing between the bars? The advantage of the spacing between the bar is that concrete can flow around these bars. And then, if you remember, we said in the beginning today that steel and concrete must have a very good bond. Steel and concrete can have a good bond if concrete can flow very well around each and every steel bar, and this will be possible if there is enough space between the steel bars. Okay. So, although the ACI code recommends 1 inch spacing, I would recommend to you 1.5 inch spacing at least, because most of the time, especially in small projects, the vibrators are not available, and if there is no vibrator, then and if the concrete is very stiff and dry, it will not be properly placed between the steel bars, and there is a possibility that bond between steel and concrete will not be very good, which can put the beam in, which can put the beam at risk of early failure. Okay. Then, depending on these, then this thing, when the spacing is at least 1.5 inch and the cover is this will basically restrict the maximum number of bars to be placed in one layer or one row of reinforcement. Okay, this will fix the maximum number of bars. These maximum number of bars are then given in this table. If beam is 12 inch wide and you are using number 5, number 6, number 7, let's say number 8 bar. So maximum 4 bars can be placed inside this beam in one row, in one line, in one row. If you need more bars, you can place it in another layer, another row. Okay. For these different widths, the maximum number of bars are given in this. These are the diameter of the bars, number of bars, bar numbers, and these are width of the bar, and these are the maximum number of bars that can be placed. For 14, 16, 17, 18, in 18 inch wide beams, if you are placing number 8 bars, so maximum number of bars that can place 7. But these maximum number of bars are placed on the criteria of 1 spacing, and I said that the maximum number of bars shall be calculated based on the criteria of 1.5 inch clear spacing, which will further reduce the number of bars in one layer. There is also a criteria on the minimum number of bars in one layer. And the ACI code required that at least 2 bars will be placed. At least 2 bars shall be placed in one layer always, regardless of the width of the member. But up to 15 inch, the 2 bars are required, and more than if the beam is wider than 15 inch, then 3 bars will be required. And there is also a table for this. This table is given. If the beam is 12 inch wide, then 2 bars, 14, 12. If the beam is 16 inch wide, then at least 3 bars will be required. At least 3 bars will be required. Okay. Okay, if bars are to be placed in a second layer, then every bar shall be placed on top of the bars placed in the bottom layer, and then okay, so if I think you have another class, so we will leave this lecture at this slide number 45, and we will continue this lecture inshallah next time. Okay, thank you. Allah Hafiz. If you have any question, you can come up with your question next time. Okay, and I apologize for starting the class late today due to a meeting, which was also very important meeting with the education department. They were basically doing a project on the school structural health assessment. So I was there. Okay.
Okay, sir. Thank you, sir.
So we will discuss the remaining part of this lecture, inshallah, next time. You can come up with questions next time. I will appreciate asking questions. Okay. Thank you. Khuda Hafiz.